So we are considering, just for recapping, we are considering the problem of the computation of the gradient of the error, which is used for finding the, as is shown here, the optimal, let's say, the optimal value of the weights which represents the final training of, at least this should be the target, so the final value of the weights. So normally this is as we saw a few slides ago, it was performed by computing the gradient of the loss function. Well, normally this gradient is, so as is written here, so as we also I anticipated in the previous slides, the update rule for computing the weights is represented by this cost function here, or this is called also adaptive law, because it means that the new value of the weights is correspond to the previous updated with respect to this term, which contains two factors. The first one is defined as a training rate, because as you can see here, depending on the value of this parameter, which is a real value, you can improve or decrease the updating of your weights, and this is the gradient of your cost function computed on the previous value of the weights. And as you can see here, the dimension of this gradient depends, of course, on the number of the derivatives. So if normally the number of weights is important, so also the dimension of your gradient can be important. So it means that if you are using a classical, let's say, gradient descent, and normally you need to compute the gradient of this cost function computed for all, as you can see here, for all the possible number of samples, the data that can, which is indicated here by the number, is represented by the number capital K, and K is what we call the size of the database, so the number of samples. Normally in neural networks, the number of samples has the order of several, let's say normally can be bigger than normally, let's say 10 up to 5, so it's not impossible to work, for example, with million data, so it's a normal number. So it means that also the computation of your gradient can be computationally expensive. So it's why in some cases, or in order to reduce the computational complexity, we are considering the stochastic gradient descent. So stochastic gradient descent means that we are computing, we are evaluating our cost function. So it's why we are using here the notation with the cap as a hat for a reduced number of the original batch size, which is so normally can be of several hundred, so it's much cheaper than in terms of computational complexity. So as is written here, so the computation of a stochastic gradient descent can be, as is written here, of the order of several hundreds of data, in contrast to the value of normally 10 up to 4, so several thousand against several millions. So, and another important point is that the data points should be identically distributed, so they should follow an independent statistical distribution. And this is another requirement when you are acquiring the data. And of course, could be an important problem when, for example, you are performing an online learning. So it means that you want to implement your estimation. So normally, all these solutions are performed offline, and perhaps once your network is trained, so you can implement it online. But so once only so the training phase is performing offline. But in some adaptive cases, you can consider also the online implementation, even this is not so common. And in this case, as you can see here, depending on the gradient, so normally the update step, which is represented by this arrow here, red arrow. So the update strength, let's say, we can say here, depends, of course, on alpha, this parameter, and also on the gradient. So depending on the value of the gradient, the step size, which is used for updating your parameters, can be also very small, especially for example, in this case, when the gradient of your function is very small. So this adaptive law, here is one. If the gradient is very small, takes a lot of time for updating and go to the right direction. So for example, in this case, to find the global minimum of your cost function. So in order to improve the computation of your gradient, you can, just a remark, and especially because this approach is implemented in MATLAB. So normally is that you are not using a simple gradient descent, so it's like something which is represented in this equation, so which takes into account only the first derivative, but is including the Hessian of your cost function, which is the second derivative. The problem is that a second order gradient method, so is including not only the computation of the first or the gradient, but the computation also of the second, so the second derivative, and also the inverse of this cost function, and on the inversion of this matrix. That you know that perhaps the inversion of a matrix can be computationally expensive, especially if the size of the cost function is, if the size of the matrix is important, is big. So if you, in this picture, when you are considering also the factor which includes the second derivative, so the Hessian, in this picture means that the update of your weights can be improved. In fact, the step increases. So it's why normally the second order gradient methods improves also the updates of your algorithm. And there is another problem when you check, for example, the step size and the computation of the step size. I'm going back because, as I mentioned, the update of the weights depends also on the learning rate. So it's something that can be updated online. In fact, this parameter is automatically updated when you are considering the algorithm, that the optimization procedure that are available in MATLAB. So it's why this is another picture here, which shows that, for example, when the learning rate is quite high, in a gradient descent, as you can see here, let's say the dynamics of the algorithm can be oscillating, because as you can see here, the algorithm tries to update your parameters, your weights, but because the learning rate is quite high, so the update is quite high. So instead of following a smooth trajectory for the update of your weights and go to the minimum of your cost function, you are oscillating around the minimal values of your cost function, and it takes longer to have to go to the global minimum. So there is just to mention, there can be more complex procedure that I don't want to show here, which includes, for example, the problem of the oscillations, and try to reduce the effect of the oscillations in the learning, in the optimization of your weights. In fact, in the, I don't know if we have time in the last two lectures, in the next days, but we can examine an algorithm that can show you an algorithm that is used for optimizing or for finding the parameters of a neural network. And it includes a term that in the optimization algorithm, which is called momentum. Momentum is another change in this adaptation rule, which includes also the history of the previous change of the weights. So it is able to reduce the oscillation in these cases when for example, the gradient is too high, and so is able to stabilize the algorithm. So before closing this lecture, this part of the lecture, I want to summarize the most important parts of this first module regarding neural networks. So we examine the structure of a neural network, which depends on, so starting from a neuron. So the single neuron represents let's say the simplest module or block for obtaining a complete neural network, a more complex neural network. The neuron can be represented by an activation function, which can be highly nonlinear for the case of, for example, of the input and the hidden layer, and it can be linear or linear rectified for the output layer, depending on the task of the neural network. And the learning of a neural network is recasted into an optimization problem, because the learning of a neural network aims at finding the optimal weights of the network, which minimizes the cost function. So the cost function is represented by the difference between the output of the neural network, which depends on the inputs and the weights. F, of course, depends on the structure of the neural network, which is a function of the input. And so also the training of a neural network consists of two phases. The first one is the forward pass. So it means that the output is computed as a transfer between the input and the output of the neural network. On the other hand, we had the backward pass. So the backward pass refers not really to a transfer from the output to the input, but is really the computation. So backward refers to the computation of the cost function which starts from the output and moves to the input, because for finding the minimization of and the update of the weights of the network, you need to move starting from the output of the network, as is shown here, to the input. So it's why it's called backward pass phase, and is an important characteristics of one of the most important characteristics of multi-layer perceptron neural network, which is considered in this course. So we concluded the first, let's say, the first part of neural network by considering the structure, so the particular structure of a neuron, and then quite simply we moved to a complete structure of a neural network, and then I provide you some details on the training of a neural network. So we can move, I don't know if you, before moving to the next module, so we can see here. So by taking here so we are currently examining the structure and introduction to neural networks, and so we got some details, so I don't want to provide you a comprehensive description of the neural networks, but just to give you some general information on artificial neural networks. And then we are considering the case of artificial neural networks for control. So we can